Okay, this video is going to discuss the meaning of power, specifically power compared to energy. So I first want to look at the equation for power, and then I want to talk about the unit for power that we use in AP Environmental. The general equation for power equals energy divided by time. So it's the rate at which you use energy. That's the definition for power, the equation for power. Units for power typically are, a common unit of energy is joules, and a common unit of time is seconds. So you're talking about joules per second, and a joule per second is a watt. So this is the unit for energy, the unit for power that we're going to talk about. And of course a watt can be abbreviated W. It's not very much. We'll often talk about a kilowatt. Huge power plants, megawatts, even gigawatts. So if you're talking about the amount of power the United States can generate, you'd get into even bigger prefixes like tera and exa, and huge amounts of power. So if you look at this is just the kilowatt. This is the unit of power we're going to discuss. Remember, we already talked about units of energy: calories, joules, BTUs, and kilowatt hour. So this is where the confusion lies. Don't confuse the kilowatt hour, which is a unit of energy, for the kilowatt, which is a unit of power. So here's some examples. You can see a big coal-fired power plant might produce 80 megawatts of power. A small little wind farm may be 6,000 kilowatts of power. A big nuclear power plant may be a whole gigawatt of power. So that's the power they're capable of generating or producing. This is from the last video, the power that different machines require in order to work. So notice these are all in watts. These two could be in kilowatts, 2 kilowatts, 4 kilowatts. And that's an important thing I want you to think about, those two pictures, when you think about power. Power can be thought about both in terms of making power, making it or generating it or producing it. And power can be thought of in terms of using it or amount of power needed. So this is a big modern wind turbine. Maybe it can generate 3 megawatts of power, which would be 3,000 kilowatts of power. If we want to change that to just watts, that would be 3 million watts of power this turbine's capable of producing. And then if you look at our little light bulb needs or would use 100 watts of power. So say your town put up a wind turbine that could generate 3 million watts of power. If you look at this simple math, your wind turbine could power, it's enough power to power 30,000 light bulbs. If you have a bigger appliance, say you have a microwave that needs 1,000 watts of power, then you can't run as many. You'd only be able to run 3,000 of these with this amount of power. So that's a critical thing I want you to talk about. I want you to keep in mind that power is talked about in terms of how much you can generate or how much you need. The next thing I want you to think about is power related to energy. So if we look at this one, when you start measuring how long, and that's the key thing, the time, how long you're going to generate or use power, then you're talking about energy. So, in other words, here's my wind turbine. My wind turbine is rated at 3,000 kilowatts or 3 megawatts. Say this thing turns 365 days a year, 24/7. Obviously, it's not going to. Sometimes the wind won't blow and it'll just be sitting there not doing anything. But let's say it's running at full capacity. Then you're talking about how long is this power production occurring. So it's 365 days in the year and 24 hours a day. So you can see what's going to happen to these units. Days are going to cancel and your only units left are going to be the kilowatt hour. And now we know how much energy this turbine produces. So this turbine has this power capacity, but multiply all this out, 3,000 times 365 times 24, and you get 26,280,000. I don't fit. That's how much energy it produces in the year. So two different units, but related by how long the generation occurs. We could do the same thing for the light bulb. Say our light bulb requires 100 watts of power, and say it's an outside light bulb on your front porch, and for some strange reason you leave it on 24/7 every single day. So the thing runs 365 days out of the year, 24 hours out of a day. You never turn it off. It's the exact same calculation. Days cancel and you're left with watt hours. But we'll see. If you look at this, 876,000 watt hours, move the decimal place and we're talking about 876 kilowatt hours. So that's how the power requirement of this light bulb means it will need this much energy if you run it 24/7. Alright, so that's relating power to energy. Now I want to do a problem. If you look at this problem, average home needs 8,000 kilowatt hours of electrical energy. And actually, that's low. The average home in America needs a little bit more than that. How many homes could a 1 gigawatt nuclear power plant supply in 1 year? So again, notice these units are different. This is talking about energy needs, and this is talking about power production capacity. All right. Which means we're going to have to convert this to energy in order to decide how many homes it can supply. So our 1 gigawatt power plant, we know 1 gigawatt is 10 to the 6 kilowatts, right? Right? If kilo means 10 to the 3rd, mega means 10 to the 6th, giga means 10 to the 9th. That means the difference between these two is 10 to the 6th. You gotta know this stuff. Alright, so our 1 gigawatt nuclear power plant is the same as 10 to the 6 kilowatts. So that's 1,000,000 kilowatts. That's its power production. And let's say it runs 24/7, okay? There's 365 days in a year, And we know there's 24 hours in one day. So there's 8,760 hours in 1 year. So if our power plant, so we just have to multiply these two. Our power plant has a capacity of 1,000,000 kilowatts, and it's running for this many hours. So multiply these two together, and we know how many kilowatt hours of energy it's going to produce. I'm going to do this in scientific notation because it's easier. This is 1 times 10 to the 6th kilowatts of power times 8.760 times 10 to the 3 hours in the year. 10 to the 6 times 10 to the 3 is 10 to the 9th. 1 times 8.76 is 8.76. So 8.76 times 10 to the 9th kilowatt hours. That's how much energy. So we just converted this power capacity to total energy produced in 1 year by this power plant. So we just got to divide now to see how many homes then it can power. 8.76 times 10 to the 9th kilowatt hours. Each home needs 8 times 10 to the 3 kilowatt hours. 10 to the 9th divided by 10 to the 3rd is 10 to the 6th. 8.76 divided by 8 is close to 1. It's very close to 1. If you do it in your calculator, it comes out to 1.095. So, and notice, units go away. What's the final unit? How many homes? So this power plant can supply power to over 1,000,000 homes for a year. And that is relating power to energy. Now, the next video is going to talk about efficiency and capacity factor, because obviously this power plant is not really going to be able to produce that much energy. It's occasionally got to be shut down for maintenance or routine safety checks. Maybe it's got to have upgrades or environmental standards improved or whatever. So its actual capacity and efficiency are going to always be lower. Nothing's 100%, but for this argument, we'll say it is. All right, that's it.